So this is how you create the Lewis structure and ultimately the geometry for chloromethane CH3Cl. So first we're going to go to the periodic table and check out carbon, hydrogen, and chlorine. Notice that carbon is in this fourth column. It has 1, 2, 3, 4 outer shell electrons, or 4 valence electrons. Remember that even though it has, neutral carbon has 6 electrons, 2 of those are actually in the core electrons. They're in a lower shell than the outer shell. And that only leaves 4 behind for actual bonding and chemistry. Hydrogen has 1 electron and it's in its outer shell. And chlorine has 7. It's in the 7th column. So I just count 1, 2, 3, 4, 5, 6, 7, or I can just look and see that the column is column 7. Therefore, chlorine has 7 valence electrons. And with this information, we can go ahead and figure out what's going on in the structure. The only other piece of information you might want to keep in mind is that carbon is going to be the central atom. And the part of the reason why I know this is because of just experience. Oftentimes carbon will be a central atom. But we'll kind of look at this from more of a Lego type perspective, and you'll figure out that as a building block, carbon tends to be in the center, and other elements like hydrogen, chlorine, or fluorine, or bromine, or iodide, those tend to be terminal. And I'll explain why. But first, I'd like to count up or add up the different valence electrons to see how many electrons are going to be involved in the bonding and the Lewis structure for this compound. So chlorine, there's 1 of them in the formula. The lack of a 1 after the chlorine, like there's no number there, so that implies a 1. There are 3 hydrogens, that's the subscript to the right does. And since there's no subscript following to the right of carbon, that means that there's just 1 carbon. It's like an implied 1. So if I multiply that by the count of valence electrons for each of these elements, if I multiply the count of them times the count of valence electrons per element, I end up getting 7, 3, and 4 for the contributions of chlorine, the 3 hydrogens, and the 1 carbon. And I can add all these up and I get 14 valence electrons. So I can also think about how many valence electrons each of these elements wants to have around it to have its outer shell of electrons filled. And this is going to be the duet rule for hydrogen or the octet rule for carbon and chlorine. So I figure out that each chlorine, since there's only 1 of them, it's 1 times 8. That's how many electrons it wants to surround itself with to fill up the valence orbitals that are in its outer shell. And the same with carbon, it wants to have an octet. Each hydrogen wants to have a duet. It wants to fill its 1s orbital with 2 electrons. And if I add up just what all of these elements want to have surrounding them, I end up having 8 plus 8 plus 6, that's 22. And the difference between what is wanted to surround these elements and fill up their orbitals and what valence electrons are available is the amount of valence electrons that will have to be shared. If you don't have it, you're going to have to share it. So with that in mind, I can actually calculate the number of bonding electrons by subtracting how many electrons they want for their valence shells, subtracting from that number the amount of valence electrons they actually have, and the difference is 8. So these 8 electrons are going to end up being 4 bonds. We need to have 4 bonding electrons indicating that there's 8 shared electrons. 4 bonds, 8 bonding electrons. So next we can start drawing this, and keeping this in mind we should be able to figure out what's going on. There's another thing we can calculate, which is the number of non-bonding electrons. Those will be the electrons that are not in these bonds. So if we had 14 electrons to start with and 8 are involved in bonding, that means that 6 are going to be non-bonding electrons. So what I can do from here is try to figure out how the valence electrons are going to share or be shared between different nuclei and create bonds. And the reason why I know that carbon is going to be in the center, aside from the fact that it's the most electropositive element, or at least one of them, like carbon and hydrogen are about the same, really the reason why I know it's in the center ultimately is because I know carbon can make as many as 4 bonds, whereas hydrogen and chlorine typically don't make more than 1 bond each. They tend to be terminal. So for example, chlorine, it just needs one more electron to fill its octet. So if we just share an electron from some other atom, chlorine and carbon for example, and make a bond, you'd find that now chlorine's octet is filled. So chlorine probably, most of the time, is not going to do much more bonding than this. It doesn't need to. There are a few exceptions to this, but overall, if I had to guess, I'd start by saying that the chlorine is terminal. And I need compelling reasons to the contrary to say that it's not. Similarly, hydrogen tends to be terminal as well, because with just one bond, if I take these 2 electrons and turn them into a bond, now there is a complete valence shell for hydrogen because it has 2 electrons from this bond surrounding it. It's done. It's filled its duet just with 1 bond. So it's going to be terminal. It's not going to bond to other stuff and form more than 1 bond. And this is going to be true for all these hydrogens. So that is the Lewis structure for chloromethane. We can use this to figure out what the geometry is going to be. If you look, you can see that there are 4 places where there are electrons around this carbon. Here, 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 and here. The only places are these single bonds. So what that means is that this is going to be tetrahedral because it has 4 places where there are electrons around that carbon. So tetrahedral geometry will look something like this. So here is the structure, the geometry I should say, for chloromethane. And I gotta fix this. So there should be 3 hydrogens. There we go. So if we check everything, it should work out. We have 3 hydrogens and 1 chlorine, 1 carbon. 3 hydrogens, 1 chlorine, 1 chlorine, 1 carbon. That's good. We also have this tetrahedral geometry. The bond angles are going to be about 109 degrees. And we also can check the counts of bonding and non-bonding electrons and total valence electrons to just make sure that we haven't done anything nuts. So if I count the number of non-bonding electrons, there's 1, 2, 3, 4, 5, 6. That's consistent with what we predicted using just a little bit of math. There are 4 bonds, that's 8 bonding electrons. That's consistent with what we predicted. And if you add those 2 together, you get 14, which is the number of valence electrons we started with. So that's how you do this. It's really pretty straightforward, and there are a lot of examples of carbon-based molecules that have 4 substituents like this that end up having a tetrahedral geometry and 4 bonds